Okay. Okay, let's look at this. Impressive matching.
My wallet matches too. Seriously, it's teal with like crossed crystals.
Wow.
Yeah. It's pretty
I'm
impressive.
speechless. Okay, here we go. So let's look at this first before we do anything. We saw an example yesterday where we started a new habit. We're always going to look for restrictions on the domain, right? So we probably want to rewrite this as a fraction. It's always convenient to have it written in fractional form when we're looking for restrictions, because then we go straight to the denominator, right? So that just looks like 6 over the quantity x squared plus 3. Okay, here's my question. Is x squared plus 3 anywhere 0?
Yes.
Where? Okay, but the square root of negative 3 is not a real number.
No, it does not.
Right? Okay, and when we're talking, we are presuming our domain is the set of all reals unless otherwise, unless there's some other restriction. Well, unless we're going to say something else specific, but you guys are not going to do calculus with the full set of complex numbers, including imaginary numbers, for quite some time. And that won't even be probably, it's going to be matched.
I'm sorry.
Probably not until second year calculus, probably. So I mean, you got a little ways to go for that. So we're always assuming the set of real numbers, and x squared plus 3, there are no real zeros of that expression, right? We said it, and how do we know? Just real quick, how do we know that?
We don't.
You can't factor it.
If we set this equal to 0,
We're gonna get a plus or
You don't have
minus.
you can't
You
factor
get
it.
imaginary.
okay, say it again.
Yeah.
Okay, you can't factor it. There's a bunch of reasons to justify why there are no real zeros to this. One of them is, probably the easiest one is, if I just look at what's going to happen, if I do one thing, if I ever have x squared equal to a negative number, we know right there off the bat, you can't square root a negative number. That's one of our 2 fundamental no-nos for real numbers, right?
Oh, but then you get imaginary.
Right, but those aren't real, right? So that's one way to tell. What if it were a more complicated quadratic expression, though? What if it were something like this? What if it were, just hypothetically, what if it were x squared plus 2x plus 7?
No, just can't. 2 also helps. No, that would work, right?
How would you know whether or not that had zeros? Pretend that was the expression on the bottom, and we needed to know if it had zeros.
Solve for x.
Yeah, solve for x. But there's a really important shortcut here when you're looking to determine if a quadratic expression has zeros.
Factor
Yep.
all the components of their positive.
No, it's not even that. It's not even that. It has to do with the value of the discriminant. Do you remember that from a couple years ago? Okay. Okay. Go ahead, Anna. Say it again.
The square root being in the quadratic.
Exactly. It's the argument of the square root in the quadratic formula. And we all know the quadratic formula.
X equals negative b plus or minus square root b squared minus 4ac
Oh, there it is.
divided by 2a.
Okay, so,
One more time.
yeah. So the square root part is b squared minus 4ac, right? So,
I like the one more time.
okay, because
There's no much thinking.
it was beautiful.
Hi, Sarah. Make good choices. Make
This
mediocre choices.
is a good thing to say once in a while.
Okay, so we know this is the part under the radical, so this is the part that has to be positive, or has to be non-negative, can't be negative, in order to not break that rule for real numbers, right? And so it is negative, we can see that. 2 squared minus 4 times 7 is clearly negative, and so we don't even have to bother doing anything. We just check the value, check the sign of the discriminant, and if the sign of the discriminant is negative, you know you have no zeros, and done, right? Okay. Okay, so back to business. Ours wasn't that tough though. So there are no zeros of the denominator. Whoops, I'll do that. There we go. So our domain is unrestricted, right? So we're gonna be able to look for critical numbers anywhere, okay? No vertical asymptotes, right?
Yeah.
Because the bottom is never zero.
Yeah, but you can't divide by a negative number, isn't that undefined too?
Not
You
divide,
divide by
sorry.
Right, exactly, okay, but my point is there are no x values that would ever make,
An asymptote?
there are no x values that could ever make this zero, right? Because if I try to solve, if I set the bottom equal to zero, really what I'm doing is I'm just asking, if I set the bottom equal to zero, are there any solutions to that? And if there are, those would be asymptotes or holes, right?
Mhm.
If I set the bottom equal to zero, there's no real solutions of that. Therefore, there are no zeros at the bottom, so we can't have any vertical asymptotes. And there are no square roots in the bottom, are there?
No.
Right? So we're home free.
Okay.
Okay? All right, so then what's going to be our next step?
Differentiate.
We're going to differentiate, take first derivative. Okay, so we're going to, and we want to use probably this form, don't we?
Wait, why don't we just use the quotient rule?
Okay, now somebody help us out. Why do we not use the quotient rule?
Just too much work.
Because it's unnecessary work, because we only use the quotient rule for a quotient of functions, right? If we use the quotient rule here, what's the derivative of 6? Zero. So why use it? You know what I'm saying? We would never use the quotient rule unless we needed to, which meant we had a function divided by a function, right?
Yeah. Oh my god.
Okay, but we've got some stuff going on here. I've got a constant 6 out front. At the outer level, what kind of rule do we follow here? No.
Keep that.
We don't need a product because 6 is a constant.
We just use
Yeah, we should have a power rule, right?
Yeah.
So we have hand to the -1. The derivative of hand to the -1 is
negative hand.
negative hand to the
Two.
-2. Okay, so that's going to give us a -6 x squared plus 3 to the -2, but we're not done. Times.
2x.
Okay, so that equals -12x times x squared plus 3 to the -2, right?
Yeah.
Let's go ahead and write that as a quotient also. So we'll write that as -12x over x squared plus 3
Where'd you get the 2 from?
squared. Because we have to differentiate what's inside by the chain rule,
Okay.
right?
Yep.
Okay. So now we have to, there's our first derivative. We need to find all critical numbers. So critical numbers exist where the derivative is undefined or 0. So is this derivative undefined anywhere?
No.
No, and it's not for the same reasons that this wasn't, right?
Yeah.
The function on the bottom is just an x squared plus 3. So what if it's squared? Still, the zeros of the bottom would be when the zeros of x squared plus 3. And we already determined there aren't any, right? Okay? So it's nowhere undefined. Where does it equal 0?
That's 0.
At 0, right? Wherever the numerator is 0, and that's clearly at x equals 0. So let's make our table.
Love those tables.
Yeah, no tables.
Isn't it just 0?
I have a question about the table.
Yeah,
How come on X, whenever you draw it, that you give it the arrow and then the other line?
because it's just the x-axis. See what I'm saying?
Yeah.
And so when you do this table, these are really just like the values on the x-axis. And so I'm getting you in this habit because when we get to section 3.6, which is curve sketching, then all you have to do is just use this information and just draw it above the table, right? See what I'm saying?
Yeah.
Okay, so so tell me what's going on here. When x equals 0, that's an important point. Why?
Critical number.
Okay, how do I know that?
It's there. Or is it 0? 0 pretty much usually.
But what's telling me that in the table tells me everything. Okay, f prime is 0, right? Okay, while we're at it, what is the value of our function when x is 0? We might as well, it's easy. 2. So we've got the point 0, 2, right? Which is a critical number. So how are we gonna tell if this is test points? There we go. So what are we gonna try?
-1
And-
+1.
Okay? At -1, let's look at the sign of the derivative. Now let's play our sign game. We have this factor. So, can anybody tell me, hey, don't talk please. Can anybody tell me what is the sign of the bottom always and why?
Positive, because you're
How come?
squaring it.
Because it's something squared. So it's always positive, right? Okay, so really all we have to do is determine the sign of the top. What's the sign of the top when x is negative? Positive. How about over here?
Negative.
Okay, so the first derivative test tells us that we have what?
A maximum.
A maximum. Okay, very good. Okay, we're gonna redo this. I'm gonna show you another way that you can get the same information and more. Oh, and by the way, on what intervals is this function increasing?
Negative
Negative.
To 0, decreasing.
Increasing at 0
There's a positive.
Wait,
Good.
so do you include parentheses or brackets?
Parentheses. So if we, so let's write that. So,
Wait, yesterday, right, you said, that when it has the S curve, right?
Mhm.
That it goes like this, but it never actually changes, it just goes to 0 and then it starts going up again.
right.
You said that like 0, it would be increasing there, so if it's, or like you argued that it did actually have a slope there since it's only a single point, so.
Right.
For this, why wouldn't you include like the brackets for 0 in this?
Because in this case, it's not. In this case, that is a point of transition.
Yeah, but isn't it like, if both sides on it are, have a slope, then one, by the like same logic, wouldn't it be increasing?
Okay, yeah, but what's the slope of this point then? If the point to the left is below it and the point to the right is below it, doesn't it,
Couldn't you
the
have
limit
both?
goes to 0? See what I'm saying?
But I don't, like, why couldn't you have brackets, like have it included in both?
Well, for one thing, you can't do that. You can't double count a value. So
Well,
you
yeah,
have to, so there's another argument against it, because it has to get included in one of them, and so which one should it get included in? They're completely symmetrical.
Why can't you have them included twice?
Because then you could have, for example, well, how can a function be both increasing and decreasing?
Well, how can it not be both not increasing and increasing?
Okay, because this one is, there's undebatably, because it's actually a horizontal tangent, the value of the derivative is 0 there, right? So the instantaneous rate of change is 0. 0 is the boundary between negative and positive. And so that's the reason that we say that this is, it's a boundary value, but it's not included. Okay, the other one is debatable. I mean, you could argue both sides of it.
But like on the other one, the argument was that on both sides, like both points next to it, it's an increasing
Well,
value.
don't both points
It's only a
have the
single,
same slope?
and it's only a single point that supposedly might not have a slope to it. Or a 0 slope. But then in this case, like this one doesn't, on both sides, it has a slope.
Okay, but the thing that we're missing here, and this is the, I didn't reveal this is the strong argument why you wouldn't include the other point, and that is because if you actually take the limit of the slope, it's 0 in both cases. And so you really can't say, I mean, that would be the argument someone would say, well, that other point then does have a slope of 0, so you'd have to exclude it. But it's just kind of a meaningless thing to exclude, being as, in that case, because it's increasing or decreasing on both sides. So it doesn't really separate anything significant. I mean, honestly, we could probably, if we wanted to, this mathematical discussion, if we wanted to really get sophisticated about what I was saying yesterday, we could probably spend like 6 hours talking about it and bringing up valid points. But that one is slightly debatable. This one would not be though. This one is clearly, it's a 0 slope. Okay. Okay, so now I want to just copy the top of this thing, and we're going to go back and we'll show you something a little different approach to this. Let's do this. So we've already done all this work. We don't have to redo it. Did I? Okay, so there's our stuff. Now let's just see what would happen if we took a second derivative. Okay? So we rewrote this as a quotient. Let's just go ahead and use the quotient rule. And by the way, this is not necessarily one where we would maybe choose to do the second derivative because it is a quotient rule. We're going to force you to this time. So what is f double prime of x? We're differentiating this. So I could pull the negative 12 out front, right? Let's do that.
As long as we don't have to do two variables.
Wait, we're not doing the question rule?
No, we are. So we're just going to do the quotient rule. Okay, so then we're just taking the, pull the constant out front. We're doing the quotient rule for that function. So what are we going to get?
X. Oh, not
X squared times 1 minus x times
2x
times 2x. Because I have to do the derivative of what's inside. Chain rule. Gotcha. Divided by?
It would be b squared. So x squared plus 3 to the 4.
Good. Okay, because a power to a power means we take the product of the powers, right? Okay. All right, so there's a couple things we got to be aware of here with this now. So if we clean this up just a little bit, but not too much, I'll tell you what. Last chapter, when we took derivatives, this would have almost right there been enough for your answer, wouldn't it? We didn't have to do a lot of cleanup work last chapter. We didn't have a need. This chapter, though, we're going to have a need. So I'm not going to tell you quite why yet, but let's just kind of just follow my lead a little bit here, and then later on we'll come back and talk about why. So we've got a minus 12 times on the top, times the quantity x squared, oops, plus 3, I don't know, squared, minus 2, or 4x squared,
Yes.
times,
Wait, how did we get that? Why wouldn't it be to the 4? Oh.
I didn't distribute.
Oh.
Notice I kept that x squared plus
I
3
see.
separate.
Okay.
Okay, and there's a reason for that. Okay, I'm going to put a star by that because there's a reason for that we'll see. All divided by x squared plus 3 to the 4th. Okay, so let's talk about the meaning of this second derivative for a second. We're going to move away from the problem and we'll come back to it. But let's talk about what the meaning of a second derivative really is. Okay, so I'm gonna leave this, we'll come back. But let's kind of go back to the relationship between the various derivatives. So if I graph, for example, you could tell me if this is my original function, let's say, so that's f. What's the graph of f prime going to be?
Straight line.
No.
Okay, how would what are the points that, if we're going to graph the derivative of f, what are the points that we could pin down right away?
0.
So like it would cross the x-axis where the slope of the very original function is 0.
0. Okay, so we look for horizontal tangents. So right there we know the slope is 0. So the value of the derivative must be 0. Right there we know the slope is 0, so the value must be 0. And then we're just going to kind of use those points to anchor our sketch, and then just think about, where's the slope positive, where's it negative. So what's the value of the slope on this side? Positive, and it's very positive. From left to right, it's getting less positive, isn't it? So that looks kind of like, maybe like that. Okay, same thing now down here, it's slightly negative, very negative, less negative, right? So it's kind of doing something like that. And then up here it's doing something like that. I probably didn't get the scale right. You get the idea, right? Okay, let's look at the second derivative. Now, if I want to graph the second derivative, am I really looking at the blue graph or the black graph most conveniently? The blue graph. Because the second derivative is just the derivative of the first derivative, right? So here's what I want you to keep in mind. You already know this. First derivative is to the function as the second derivative is to the first derivative, right? Okay, so you see they have that same kind of relationship between, right? So if we graph the second derivative then, we've only got one spot where we have a 0, and it's going from being negative to being positive, so it's going to look, we would expect it to look something like that maybe, right? Okay. All right, so.
That's the third one you said?
Mm-hmm. Okay, now I want to see if we can relate, here's the trick. I want to see if we can relate the value of the second derivative to the shape of the first derivative. And that's a little bit of a trick. I mean, it's nothing that we've ever talked about before. Think what the second derivative is. The second derivative, the first derivative, any derivative, is a rate of change. So the first derivative is the rate of change of the function. Now let's just explore that for a second. Let's talk about what that means. So as the ant is walking along the black function, the rate of change means how fast is the function changing? Changing its value. It's going to be changing its value rapidly when it's a steep function, isn't it? Right? Because the y value is changing. You see what I'm saying? The y value is changing rapidly here. So that means the rate of change of the function, aka the slope or the first derivative, is large, right? And we know that it's changing its value. It's getting more positive, right? As the ant walks along the black function there. And the rate is large. As he walks up towards this peak, though, the function is still changing its value in a positive way. It's getting more positive, the height of the function, right? But it's slowing down the rate at which it's changing. So the value of the blue function is getting smaller, but still positive. At the peak here is the point where now the function, at that momentarily, it just stops changing, right? And it starts to change its function now by becoming, it started to change its value in a negative sense. The height is decreasing, right? And it starts to pick up speed doing that. The rate increases. So the value becomes bigger and negative, right? And so on and so forth. Now let's look at the red function is to the blue function, just like the blue function was to the black function, right? But how does the red function compare to the black function? The red function is, now think what it must mean. If the red function is the rate of change of the derivative is the rate of change of the function. So does that make the second derivative the rate of change of the rate of change? Okay. So you tell me a place here where you think the rate of change of the rate of change would be pretty large. The rate of change of the rate of change is going to be large whenever the function is, as the ant steps along, the rate at which the function is increasing or decreasing is changing itself, right? Okay, now think what that means. If the ant were walking along a function, let's say he's walking along a function, and you're the ant who is 0 feet tall, walking along this function, looking ahead of him. If he's walking along a function from left to right, where the rate of change of the function is increasing, where as he walks to the right, the function is going to be getting steeper at a large rate. So it's a little bit steep, now it's a lot steep, now it's even more steep. What could you tell me about the terrain in front of him? As he steps forward, every step he takes, the slope is increasing, right? Because the rate of change of the function is increasing. If the slope is increasing, as he's looking ahead, what kind of feature is he looking at? Well,
He's looking at like the function.
yeah, he can see the function in front of him, unfolding in front of him, can he? Because now think what we're saying. What kind of a recipe is that for a function? If the ant is walking in this direction, let's say he's right here on this function, and as he walks forward, the slope is increasing. So when he goes to this spot right here, it's going to be that slope. When he goes to this spot right here, it's going to be that slope. When he goes to that spot, it's going to be that slope. So the ant is walking along this, well, I mean, he's walking along the black function here, but I'm making a new one for just a second. If he's walking along and there's an increasing rate of change of the slope, doesn't that mean that he's going to see the mountain getting steeper in front of him? Okay? Contrast that to if the ant is walking forward and the function, it has a decreasing rate of change, has a negative rate of change of the slope. What's that mean? Means the slope is getting more negative with every step.
Yeah.
So yeah, so he's gonna be right here. The next step is gonna be right there, and it's gonna be sloped a little bit. The next step is gonna be sloped even more. The next step is sloped even more. If he's 0 feet tall, can he see the function in front of him there? Well, it's just kind of, he just sees that it's dropping off, right? Does that make sense?
Yeah.
So he's going to be walking down the downside of a hill that's getting steeper, right? Does that make sense?
Yeah.
So we can look at this kind of topographically then, right? We said that slope corresponds to steepness of the hill. The second derivative corresponds to what we call the concavity of the hill. It's the shape of the hill. Is the slope getting steeper, which gives us this progressively upsweeping terrain, which we would call an upward concavity or a bowl up shape, right? If the rate of change of the slope is negative, that means it's going to tend to be concave down. Even if he's walking up a hill, let's say the ant is walking up this hill still, but he gets to a point here where the second derivative, which is the rate of change of the slope, becomes negative. The derivative is still positive here, right? But if he takes a step forward, it's going to get smaller positive, right? Less positive. Takes another step, it's less positive. Another step, less positive. Another step, less positive. So even though he's still increasing, the rate at which he's increasing is decreasing, right? The slope is getting smaller, and so that still corresponds to a concave down interval. Does that make sense? You get the idea? How could you, when I say concavity, are you familiar with that word? So concavity, like if you talked about, remember talking about in geometry about concave polygons and convex polygons? Convex polygons were polygons that looked like this, where none of the sides ever passed through an interior region, right? Convex or concave polygons had some kind of a dent in them. So if I continue that side, it would pass through the interior region of the polygon, right? You don't remember that at all? Yeah.
Geometry.
I do
like
for
a lot
sure.
that I remember from geometry is just proofs. This whole thing's boring.
Okay, so the other thing we talk about concave is with a lens. If you talk about like a lens or a mirror, concave lens is one that's bowl shaped like this, right?
Oh, I remember that.
Okay, so let's think of another recipe for what it means to be concave up. So this would be a positive second derivative, right? If the function, well, let's go back and look at our original function.
Wait, this one's negative?
Yeah, okay, so, well, this one's negative here, this one's positive here, right? Because the concavity changes on intervals just like the slope does. Let's look at our original function. What do you think the concavity is when the ant is right there? Positive, isn't it? It's positive because it's concave down, it's bowl-shaped down. Another way you can think about this is, would water tend to run off the surface or tend to kind of collect on the surface? It's going to be shedding the water here, isn't it? Right, and collecting the water there. Right? So that's concave up. That's concave up. Agreed? What's that? Concave up. Concave up.
That's concave. Yeah, it's concave up.
What about right there?
Think about what the ant's saying. That's concave down.
Okay, so down. This is definitely concave down there, isn't it?
Think if you're like an ant, whether you can see something or you
question
can't
mark,
see
what's
it.
gonna be concave up?
Okay, so the question mark, there's some debate there, and there's some debate for good reason, because that's what I tried to pick as being the point of transition, from being concave up to being concave down, right?
Is that what the second derivative is for?
It's, yeah, it's for all of this.
On the zero axis.
Okay, raise your hand, if you got questions, raise your hand. Right here.
How come the one above the question are usually concave up? Why is it concave?
Okay, this is concave up because it still is, or excuse me, did I say up? I meant
Yeah.
concave down.
Oh, that makes sense now.
Yes,
I was like,
Okay.
right, so these are all, right here, these are all, I'll put arrows down. Those are all concave down, right? Because the bowl is turned upside down, right? Right? Okay, listen, okay, I messed, I'm sorry about that. I was saying up when I should have said down. Concave just means bowl up, so you're asking yourself, for that part of the function, is the bowl facing up or is the bowl facing down?
Okay, so if we,
So these are bowl down, right? Concave down,
Yes,
right?
yeah,
because, okay, so we
because
drop
the bowl
water.
is facing down.
Right.
But then when we hit, if we drop water on that one point.
Yeah, okay, but this point right there, that's the point of transition, isn't it? Right?
Well, it'd be on the zero, that's how.
And these are all gonna be,
That's the concave.
was the point on the function, right? That's called an inflection point, is what we'll call that, but we don't need to worry about that for now. From this point forward, right here, the function is bowl shaped up, right?
Yeah.
So that's positive concavity. A more I tried to make it kind of visual for you, but a more mathematical test would be this. A more mathematical test would be if I drew a tangent line, in the areas where the function is concave down, the function would recede below the tangent line, right? So if I draw this tangent line here, wouldn't you agree that if I walk to the left or the right, the function is getting further and further below that slanted tangent line,
Yeah.
right? Okay, but over here, that's not the case. If I come down here when I draw a tangent line, now the function is above the tangent line, right? So it's bowl shaped up, right? Does that make sense? Okay. Notice at this point right here, if I drew a tangent line, it would be right in between if I drew that well. On one side it would be below, and on the other side it would be above. You know, when I say below and above, I mean kind of looking at it slant, right? To the left and the right, let's say. Okay? Other sides of the tangent line. So that's the transitional point there, right? Okay? So this is important. We like to know for functions, and for reasons that we'll explore later when we look at applications of this, this is another really important quantity. We want to know, obviously it's important for us sometimes to know about the values of functions. That's non-calculus stuff. To know about the slopes of functions is calculus stuff. That's important, right? Knowing about the concavity of functions is also important. One application would be like in business. Like in business, you would say that if you were, this is your profit curve, let's say. So we're graphing profits versus dollars spent for advertising or something, who knows. So if it looks like this, if our function starts to go, so we're going like this, if that's the function that we use for our model, you know, you guys are now highly paid, quantifiable, or quantified economists.
Yeah.
So you're making big money just using math to try to model the stock market or some kind of investment fund that you're looking at. So this is good, right? This is all good because our profits are increasing, right? Okay, actually this point right here, that inflection point is kind of a danger zone. Because when you get to an inflation point, that's called, in business terms, that's the point of diminishing returns. And that means that you got to beware because you're about to hit a negative, things are about to get negative. And sometimes, even if profits increase there, a lot of times, even if the profit's increasing, it's causing you to spend more money on advertising, right? And so after you hit this point, now you're starting to get less and less bang for your buck, so to speak. Right now, for every dollar you spend on advertising, the slope is decreasing, and you're getting a decreasing amount of profits. See what I'm saying?
Yeah.
So you see why the second derivative might be important, because that's what's going to tell us where this inflection point is.
That's pretty cool.
Okay. If we go back to our drawing, what do you think is the value of the function? This is really messy, but what do you think is the value of the second derivative right there? 0. It's 0. Right? That is at a second derivative critical number. Inflection points can only exist at second derivative critical numbers.
What
Okay.
happens when the slope isn't that tight? You can get that with the, right, can you do that with any form of function?
Can you do? Yeah, you can.
The square root.
You can do this. You can take The second derivative sometimes is really hard to take, and so we don't sometimes bother with it, but you can take a second derivative of just about every function you can differentiate from to get a first derivative. Okay. I can't right now think of an example where you wouldn't have a second derivative, but you would have a first derivative.
What if the second derivative equals 0?
What's that?
If it equals 0.
Okay, so now look. So would you agree that this is the dividing line right here? This is the value, this is the inflection point. This is where the value of the second derivative is 0, is right at that vertical dashed line, that x value, right? What is the value of the second derivative to the left of that? It's negative. It's negative because it's concave down. The rate of change, now listen real closely, you can't lose your train of thought on this. You gotta really think hard. The rate of change of the slope is negative because as an ant walks from left to right, the slope is decreasing, right?
Yeah.
Okay. In other words, tangent lines sit on top of the curve on that interval, right? So over here we would say that f double prime, the second derivative, is less than 0. On this side, the function sits on top of tangent lines, which means that it's the rate of change, or the slope, is increasing as we walk from left to right. So on this side, we'd say the second derivative is greater than 0.
Is that why one side is below and one side is above?
Yeah, exactly. That's why the curve sits below the tangent on this side and on top of the tangent on this side. Got it? Yeah. Okay. So now let's go back. Let's go back to our fancy function that we had here, and let's add another row to this, because this gives us. I think I told you once before. We're getting close, aren't we?
Yeah.
I think I told you once before that the further you work down the table, the more efficient it is, right? So we went through the hassle of calculating our second derivative. Let's go ahead now, because we're trying to find zeros of the second derivative. We don't want to simplify this. When we're trying to find zeros, we do the opposite of simplifying, right? Or expanding at least, we factor, right? So on the top of this thing, there's going to be a natural tendency for you guys to want to distribute that 4x squared, but don't, because look what you got here. You got a gold mine. You've got common factors, right? So I've already got them factored, in fact. So we'll go ahead and pull those factors out. We'll factor them out, and look what happens in the numerator then. You're going to get negative 12. I'm going to factor out. Now, what's the biggest common power of this factor? 1, right? I've got, listen please. Okay, I've got a power of 2 here and a power of 1 there. Well, obviously I can't take a power of 2 away from a power of 1 without invoking some kind of a fraction or something, which we don't want to do. So I can only continue this tomorrow.